Hey everyone, and welcome back to this class, Advanced Convolutional Neural Networks. In this lecture, we are going to look at the code for doing transfer learning with VGG on the Fruits 360 dataset. The first thing we're going to do is limit the size of our dataset, just so you can see this working. To do this, you'll want to run the script make_limited_datasets.py. What this is going to do is select a subset of the total number of fruits, make symlinks to those folders, and then we're going to run our script loading the data from the symlinked folder. So to start, we'll be looking at 3 fruits only. So I'm going to select raspberry, banana, and strawberry. Next, we want to go to the main file for this lecture, which is usepretrainedweights vgg.py. So at the top we have a list of paths to our data. You'll see multiple paths here because later in the course we're going to look at some different data sets. For now we'll be focusing on the fruits dataset, but you're free to jump ahead and try other data sets if you want. It involves nothing but commenting out the old dataset and uncommenting out the new dataset. Next, we're going to use the glob function to grab all the images that match a string pattern. So recall that this reflects the structure of the dataset which we talked about earlier. Within the training and validation folders, you have a subfolder for each class, and then within those, you have the JPEG files. Remember that JPEG files can have the extension JPG or JPEG, so we need to be able to capture both. Next, we do the same thing to get all the actual folders. This is so we can easily get the number of classes later in the script. Next, we have some code to look at an image just for fun. We can use the built-in Keras image module to do this. We just call the loadImage function and pass in a file name. We use np.random.choice to randomly select an image file name from our list of file names. Next, we create our VGG model, which automatically loads the pre-trained weights. So let's talk about some of these arguments here. Recall that with libraries like Theano and TensorFlow, we need to specify the input shape of our data. Since the backend of Keras is either Theano or TensorFlow, we need to do the same thing here. Technically, you can specify the image dimensions as none to allow for images of arbitrary sizes, but this requires us to use another special technique later on. We'll discuss how to do this later in the course. The next argument we want to look at is the weights argument. This allows us to specify which pre-trained weights we want to use. For us, we're just going to default to ImageNet. You could even start from purely random weights if you wanted to. Finally, the last argument here is includeTop, which we are going to set to false. This is because, as we discussed in the lectures, we want everything except the last layer of VGG, since we'll be training our own final linear classifier. Next, we have some code to make it so that we do not train any of the VGG weights. We want to train the logistic model only. This is very simple in Keras. You just set the trainable attribute to false on each layer. Next, we use the Keras functional API to add more layers to the neural network. To do this, we just declare a flatten layer, pass in vgg.output as input, and assign the return value, which is the output of this flattened layer, to a variable called x. This is standard notation in Keras, where you just call everything x. Next, we pass in x to a dense layer, of which there is only one because this is logistic regression, and we give it the softmax activation because that's what we use for multi-class classification. We assign this to the output variable prediction. Note that you can also add more hidden layers if you want to. Next, we create a new model instance and pass in the input and output. The input is just VGG's input, and the output is the prediction variable we just created. Now the next step is optional, but I think it's helpful to do in pretty much every script, and that's to call the summary function. This is going to print every layer of the neural network to the console. It's going to tell you its type, size, number of parameters, and so on. Finally, we call the compile function. This is where we pass in the loss function to use, which optimizer to use, and any metrics we want to calculate when we're doing gradient descent. In this case, accuracy. Next, we have some code that might look a little strange at first. The gen variable is an object, which is an instance of image data generator. A generator is something in Python where basically you can loop over it. But the object itself is not a generator. How we get a generator will be shown later. When we create an instance of image data generator, we pass in a bunch of arguments that tell the generator the ways in which it's allowed to modify the data. We like to do this with images because it helps with generalization. For example, we know that if we flip a picture of a dog, that it should still be categorized as a dog. We can't do something like this with e-commerce data, for example. I can't suddenly change your time visited on my website from 12 noon to 12 a.m. because that could have a significant impact on the outcome. But for images, these transformations are invariant. So the next thing we're going to do is see how this gen variable works. Now remember, you are very welcome to paste this into your Jupyter notebook as we go along so you can observe the results. Remember that I want you to code how you like to code. So testing out this gen variable at this point allows me to accomplish a few things at the same time. First, it allows me to show you how to get an actual generator. In this case, we want to call the flowFromDirectory function. This is a special function that's going to look for images with the precise folder structure that I described earlier. Remember, that's each class being a separate folder, and then all the images belonging to that class within the respective folder. This function also allows us to pass in some parameters like target size, which is a convenient way to resize all the images to something your neural network can handle. We'll see some other possible arguments to this function soon. Next, we have a function that we can call in this generator that will return a dictionary where the key is the class name and the value is the class index. So the class indices, as you know, will just be integers from 0 to k-1. Later in this script, we'll need to make use of the opposite mapping, so from class index to class name. So that's what I'm creating this labels list for. The final thing I want to test with my test generator is that the data has been pre-processed properly. You may or may not have noticed that I passed in an argument into the image data generator constructor a few lines up. Now, why do we do this? So essentially, a lot of the pre-trained weights that other researchers have released were written in different libraries. VGG specifically was written in a library called Caffe. In their particular setup, the VGG authors use the BGR format for representing images, rather than RGB, which is typically more popular. So one thing this function is going to do is reorder the channels. In addition, they also subtracted the mean pixel intensities for every channel from each image. And so Keras provides a function called preprocess input that we imported above that we want to pass in here. Now note that every built-in neural network has its own version of preprocess input. So ResNet has one, and so does Inception. So getting back to our little test, what I want to do is just plot the first image from the dataset to ensure that the colors look weird. If the colors do look weird, that means the channels have been reordered successfully. We can also print the min and max values of the image. They should not be 0 and 255, but rather in the negative and positive mid-100s. Now this lecture has been pretty long already, so let's take a little break here and I'll see you in the next lecture.